We're going to look at the simple and conjugate addition of nucleophiles to alpha beta unsaturated carbonyl compounds, which is quite a lot of verbiage. So let's first start with what's going to be the electrophile in this species, the alpha beta unsaturated carbonyl compound. So let's say that together. Alpha beta unsaturated carbonyl compound. And we need 3 carbons minimally to make that work. We need the carbonyl carbon itself. We need an alpha and a beta carbon, and we need the 2 of those to be connected by a double bond. So if we just flesh out our structure, here's what we have. And what we want to recognize is that the 2 electrophilic carbons, the 2 carbons that have a significant partial positive charge on them, one is obvious. That's the carbonyl carbon. But it turns out that the beta carbon also has a large partial positive charge on it. Let's take a moment and review resonance to see if we can figure out why. Draw an alternate resonance form that does not have the carbonyl bond. Well, if we wanted to get rid of the carbonyl bond and break it, we would have to give it to the oxygen. Reason, of course, being that the carbon can be electron deficient, but the oxygen cannot have an incomplete octet. So we can make a full-blown carbocation and an oxygen anion out of this. That puts the negative on the O, and it makes our carbocation carbon obviously electrophilic. But the alpha beta unsaturated carbonyl compounds have an additional resonance form. See if you can draw that. We can break that pi bond. We can move it over here to help stabilize that positive charge. That actually relocates the electrophilic center to the beta carbon. Now notice if you practice with resonance that you're never going to get that positive charge on the alpha carbon. If anything, the alpha carbon is nucleophilic. The carbonyl carbon, and we can now see the beta carbon, those 2 carbons can be electrophilic. So this all basically explains that we can make that beta carbon an electrophile, and we'll see now in what circumstances that happens. All of these reactions are going to involve either the carbonyl or the beta carbon being electrophilic. So the alpha beta unsaturated carbonyl compound is electrophilic. Now, each of these then you need an electrophiles or electron acceptors. Nucleophiles, of course, are electron donors. So we need a nucleophile. We can use all kinds of different nucleophiles here. And the question that we ask ourselves to determine the regiochemistry, or where that nucleophile is going to react, is going to be a question of whether or not the nucleophile can add reversible or irreversible. If the nucleophile adds irreversibly, which means that the nucleophile cannot be a leaving group, this is going to be your hydride nucleophiles and your carbide nucleophiles, notably the organometallics that are not stabilized by resonance. Then your nucleophile is going to do what we already know it will do, which will be to add to the alpha carbon, and that's nucleophilic acyl addition. That's what we would also call simple addition. So nucleophile attaches, pi bond breaks, we can't go backwards, and so we keep our alkene bond intact. We have a tetrahedral carbon with an O minus. We protonate that O minus at some point, and we have our nucleophile that's attached. And that's what we've already studied in the context of ketone and aldehyde reactions that are nucleophilic acyl additions. Now, in contrast, if we have a nucleophile that is capable of reversible addition, so a nucleophile that can also be a leaving group, and that's basically all the rest of them, then we'll actually undergo addition to the beta position. And this is going to give us a different style of product, so we're going to clear out some space and take a look at it. So a nucleophile that can add reversible will actually add first to the carbonyl carbon, but has a chance to play the Goldilocks game. So it can say, well, I'll try that product on for size, and then we'll attach the beta carbon. We'll move this pi bond over, and we'll break that carbon-oxygen bond, which will give us our nucleophile attached to the beta carbon, and moves our alkene over to between the alpha carbon and the former carbonyl carbon, and makes a negative charge on the carbonyl carbon. And you should recognize that. What kind of a structure is that? That structure being one where we have an alkene and the anion of an oxygen. That's an enolate. And so when we protonate that oxygen with solvent like methanol or water, or maybe even a little H3O plus workup, we're going to end up with the conjugate acid of the enolate, also known as an enol. And what happens to enols? Well, they're not going to hang around typically in the enol form for long. They tend to tautomerize to their more stable carbonyl containing counterparts. Oops, draw an H back here. I didn't really mean to. So we're doing this still as a generic structure. So all the bonds that don't have anything attached, they're just attached to something. And we've moved the H to the alpha carbon. We have the nucleophile attached to the beta carbon, which means in summary that if we have a nucleophile reacting with an alpha beta unsaturated carbonyl compound, we basically have to decide if that nucleophile adds irreversibly, in which case you were going to observe the reaction where the nucleophile adds to the carbonyl carbon, or if that reaction is reversible, in which case that nucleophile actually attaches to the beta carbon. We move the alkene over. We then end up creating an enol, which we tautomerize, and so we're back to the carbonyl being present again. Sorry, add an extra H. Just can't seem to get rid of that extra H. Now, it's worth noting that in this case, the irreversible route produces what's called the kinetic product, and that's just simply the fastest formed. The nucleophile goes to where it's easiest or quickest to react, which is at the carbonyl, and since it adds irreversibly, we're stuck there. This is also what we would call simple addition, because it's what we already know to do with carbonyls in the absence of that alkene. If, on the other hand, we have a nucleophile that's capable of reversible addition, it can pick and choose. It can add to the carbonyl carbon itself, try out the kinetic product, and then back off, go back attached to the beta carbon, which is slower, but actually produces a more stable product. Because it's more stable, we call it thermodynamic product, which in this case is the result of conjugate addition. We call it conjugate addition because you have to have the conjugated system for this to happen. To make the kinetic product, or the one of simple addition, we didn't need that alkene. It doesn't necessarily have to be there. Now, the simple and conjugate addition, we want to know those terms. The fact that the simple addition is the result of kinetic control, or is the kinetic product, and the fact that the conjugate addition is the thermodynamic product because we have good equilibrium is not something you absolutely need to know at this stage, but it's a good chance for us to reintroduce those terms. And remember, we did bring those up back when we were talking about conjugated diene systems in the very beginning of the semester.